Hello students, this is the recording for the 2C Thermodynamics lesson. Alright, so this is my contact information up here. Remember, you do get 3 attempts on every assignment. At this point, we have had 2 big assignments, the 1D lab and the 2B analysis. So if you don't do well on them the first time, make sure you try again to get a better grade and to make sure you really learn the content. We are on day 7 out of 45 of our quarter, so we're getting through the quarter. And we are going to have, we are in Unit 2. We're talking about thermodynamics, and we will be completing the 2C notes today. Some quick reminders. Remember, it is impossible to pass without analyses, labs, and exams. At this point, again, we have completed the 1D lab and the 2B analysis. They are both worth 32.5% of your grade. And remember that there's a lot of copying you can do to make sure that you get good grades on these. So for the 1D lab, all of the data is actually already given to you in the recording. So you just need to watch the recording to get your data. And I take you through every other step as well. And then for the 2B analysis, I do actually give you an entire answer to number 1. So again, you can just copy from that, and then that should explain to you how to do numbers 2, 3, and 4, which are the exact same procedure. Remember that each set of notes, remember in total notes are only worth 15%, so each set of notes is actually worth less than 4%, so they are not the priority. Remember that if you are getting 100% on your notes, 100% on attendance, and 100% on STAR 360, it's still not going to help you pass the class. You really need to be focusing on analyses, labs, and exams. That being said, STAR 360 is in fact due today, and it is worth a decent chunk of your grade. It is 10%, but again, remember STAR 360 by itself will not help you pass. Again, focus on your labs and analyses. But that being said, STAR 360 is due today. Make sure that you do both reading and math to get full credit. Remember, it's worth 200 points, 10% of your grade. And don't forget that you really should go through it at your own pace and do your best. Please don't rush through it, because the better that you do, the less required live sessions you end up having, which is to your advantage because you have less attendance required. Okay, so we are talking about Unit 2. We have been discussing phase changes in states of matter. Today we're going to take a look at heat energy, and explain how that's related to thermodynamics. So today we should be able to define the 3 laws of thermodynamics, explain what thermal energy is and how it's related to phase changes, and then explain how that energy is able to actually cause a phase change. And again, we will be completing the 2C notes. It does say 80% or higher, but remember, I am giving you all of the answers word for word, so really you should get 100%. So at this point, you do need to make sure your notes are open if they aren't already. If you're watching this, remember you can go to the Content tab, you can click Unit 2 States of Matter, scroll down, find the 2C notes, and then once that's open, remember to click Start Quiz to get it started. Remember, it's not technically a quiz because all of the answers are being provided word for word. It's just your notes for today. That being said, you can also find it in the Grades tab. Remember, links to everything are also in your Grades tab. Okay, so let's go ahead and take a look at our mind map. We're going to be talking about the laws of thermodynamics, which is how heat is going on in matter. So remember that even though matter can change form, it can't be created or destroyed. It will move to what's called a lower state of potential energy, and it is composed of particles that are always in motion. So let's go ahead and break those down. So the study of thermodynamics is the study of how heat energy moves, right? If you think about the word thermo means heat or warmth. Think about like thermal underwear are warm. And dynamics, the word dynamics means movement, right? So if you break that down, this means the study of how heat moves. So there are 3 laws of thermodynamics. The first is that the law of energy, conservation of energy, which if you take a look here, basically says that the energy we have before is always equal to the energy that we have after. Then we have the law of entropy. That's our second law, which again, we're going to go more in depth with these. But entropy says that even though the amount of energy before is equal to the amount of energy after, some of the energy actually becomes unusable to us. And so as time goes on, the amount of useful energy actually goes down, even though the total amount is still the same. And then the third law has to do with temperature, which says that at absolute 0, that's when things stop moving. But we will see that absolute 0 is currently something that is only theoretical and that we have never been able to do. All right, so in your notes, number 1 in your notes, please fill in the blank with the word moves and only the word moves. You should only fill in what's in red. Again, I am giving you the answer. Please pause the video, complete that, and then continue playing when you are ready. All right, so let's go ahead and break down each of these laws a little bit more in depth. So the first law of thermodynamics has to do with conservation of energy. Remember, the word conservation means to save. And so what we're saying here is that even though energy can change forms, right? So a tree can change radiant or light energy into chemical energy or sugar that we eat, right? Or if you think about electricity from the outlet can be changed into the motion and heat of a mixer, or electricity from an outlet can change into the light and heat of a lamp, etc., right? So even though energy can change form, the total amount is still the same. It cannot be created and it cannot be destroyed. So you can't make new energy in the universe and you can't delete energy from the universe. Instead, the total amount of both matter and energy in the universe always stays the same. So not only is it the conservation of energy, but also the conservation of matter, which we'll explain a little bit later on, that matter and energy are actually very closely related, which makes sense why they should stay the same then, right? If they're closely related, energy stays the same, matter stays the same. So again, the energy that we have before is equal to the energy that we have after, regardless of what it looks like, right? You can see the energy before looks a little different from the energy after, but the total amount is still the same. This is number 2 in your notes. Please fill in the blank with the word created and only the word created. Again, I am giving you the answer. It's in red right here. Pause the video, fill that out, and then continue when you are ready. The second law of thermodynamics has to do with entropy. The word entropy means disorder. Okay, and what this says is that disorder or entropy increases when energy changes. So again, we've been talking about how energy can change forms and how the starting energy and ending energy, the total quantity, stays the same, neither created, neither destroyed, it's all equal. However, there is kind of an important point to this, that even though the total amount stays the same, when energy changes, some of it becomes unusable, usually as heat. So as we change energy, a lot of times we say, oh, we're losing heat. This is why, for example, a roller coaster doesn't continue moving forever without us putting in more energy, because there's friction, and friction is lost energy. Again, not deleted energy, but it's lost usable energy. So as you can see here, right, the energy before, when it changes into a different type, again, the usable energy afterwards is actually a little bit less, and there's more unusable energy, which is heat. Okay. So in science terms, what this means is that as time goes on and energy changes, we have less potential energy. The word potential meaning useful energy. And this means that there's increased entropy, or again, which means disorder. So less potential, less useful energy, and more disordered energy. So this is why, for example, water flows downwards, right, instead of upwards, because going down is more disordered. Everything eventually dies, again, becoming more disordered. Batteries don't spontaneously recharge. Again, they eventually die, becoming more disordered, and things go from hot to cold instead of the other way, right? So entropy describes why things do the things that they do, and in general, they're going towards more disorder. This is number 3 in your notes. Go ahead and fill in the blank with the word unusable, meaning it's unable to be used. And then pause the video, complete that, and then continue playing when you are ready. All right, so talking a little bit more about entropy, right? So we understand that overall systems become more disordered. There's more entropy. However, a unique thing that happens here is that as larger systems become more disordered, you can actually get more order in smaller systems, right? So smaller systems can become more ordered as larger systems become more disordered. So for example, let's take the sun and the tree in this example. So the sun's energy is where we get all of our energy on Earth, basically. So the energy that we get is from the sun, and that's how the Earth survives. So the sun has a lot of energy. It goes from very high, so very high energy, to low energy, right? It's losing energy. Eventually, the sun will die, right? Which is what we explained in the previous slide, is that eventually things die. However, while the sun is dying, right, going from very high energy to low energy, a tree, which is a smaller system, can take advantage of this to go the opposite direction and to become more ordered. So the sun's becoming more disordered, it's dying, but a tree can do the opposite. It can take advantage of the sun in order to grow and become more ordered. However, the problem is that the tree is a much smaller system. And so even though the tree is becoming a little bit more ordered, going from low energy to high energy, it cannot make more energy, low order to high order. It can't actually make more energy than the sun is already losing, right? So you can see the sun is losing a massive amount of energy, and the tree is only able to become a little bit more ordered as the sun becomes massively more disordered. So overall, if you think about overall, this is a really big negative, and this is a small positive. Overall, you're still ending up with negative, right? So overall, the system is more disorganized. So even though some things can become more organized as the sun dies, overall, it still balances out to where we're overall becoming more disorganized. This is number 4 in your notes, so make sure you choose the multiple choice that says high and disorganized. Pause the video and continue playing when you are ready. So let's talk about the law of thermodynamics number 3, which has to do with temperature. And what this states is this is the theory that all motion will stop at absolute zero. So absolute zero, we use a different kind of temperature scale because this temperature scale actually starts at absolute zero. So 0 Kelvin is where is what we call absolute zero, and this is where all motion actually stops. So all particle motion stops completely. And in our terms, in the US, this would be negative 460 degrees Fahrenheit, which would be extremely cold. Now, the thing is that even the coldest particles, like the frozen stuff in your freezer or the frozen stuff in like the Antarctic, even the coldest particles actually still have some motion. Remember that all particles, all atoms, all molecules, everything is still moving slightly, even when it's cold. It's just kind of vibrating in place, right? So they're just vibrating in place. But again, if you were to zoom in to a molecular atomic level, you would be able to see that they are moving slightly. Now, the problem is that even in reality, in real life, scientists have not been able to reach absolute zero. We can't reach it. And the reason for this is it has to do with how heat moves. Remember that heat always moves towards colder areas, towards where there's less heat. And so what would need to happen is in order to get all of the heat out of something, like let's say, for example, we have we're trying to get all of the heat out of these packages, we would actually need to be able to remove heat into the freezer. But again, in order to remove heat, we're going to go from something that's hotter to something that's colder. So this needs to be colder. So what this means is in order to get these down to absolute zero, we would need to be able to remove all of the heat into something that's colder than absolute zero. So in order for us to get to absolute zero, we would need a freezer that can get colder than absolute zero, which would be less than what the absence of all motion is, which is not possible according to what we know with science right now. So we haven't been able to reach absolute zero. We've been able to get really, really close, but never able to actually reach it yet. All right, so in your notes, please fill in the blank with the word Kelvin. Make sure you spell it correctly, Kelvin, as you see it up here. Pause the video, continue playing when you are ready. Okay, so now we're going to go ahead and talk a little bit about how heat or thermal energy is related to phase changes. So remember that during phase changes, the actual particles stay the same, right? We talked about how even in frozen water or ice, it's still H2O particles. Even in liquid water, it's H2O particles. And even in gaseous water or steam, it is still H2O particles, H2O molecules. So what's happening here is the particles themselves do not change. It's always H2O in this example. The only thing that does change is how they're actually interacting with the other H2O molecules or the other particles in a different example, right? So during a phase change, the molecules, particles, atoms, whatever, themselves do not change. The only thing that changes is how they're interacting with the other particles, atoms, molecules in their situation. So for example, in solids, the particles are just vibrating in place next to each other. Okay, in liquids, the particles can actually move past each other and they can flow, which is why liquid water, the water moves around. And then gases, the particles can actually escape from each other, right? So we know like gaseous water or steam, the particles actually move really far away from each other and they interact much less with each other. So this being said, we talked about this already about how energy is related to these phase changes. So again, particles can gain or lose thermal energy. Another word for thermal is heat. And remember, thermal or heat energy is just the measure of the motion of the substance's molecules, right? So as we get more thermal energy, we get more motion, right? So we add thermal energy, we get more motion, which is why we can go from a solid where the particles are just vibrating in place to a liquid where they can move a little bit faster and move past each other to a gas where they can move very rapidly and escape from each other. Versus losing it, removing thermal energy means you're removing heat. And again, thermal energy is just motion, right? Thermal energy is just motion. And so if you're removing thermal energy, you're removing motion and things get slower. We go from a gas slowing down to liquids where they can only just move past each other but can't escape, slowing it down even further to solids or ice where they are stuck next to each other, vibrating in place. Okay, so let me go ahead and show an example of this for you. I'm going to go ahead and show you this right here. Okay, so if we take a look at phase changes, all right, and we were to heat up this ice right here, you can see, right, that originally they were very, very rigid, right? So again, if you cool it down, you can see how they stay very rigid, they stay next to each other, those are solids. As they get warmer and warmer, they begin to spread out, and at some point they actually begin to flow. Right? So you can see how they begin to actually flow. But again, the particles themselves are not changing. In this case, this is neon. So the particles themselves are not changing. And as they get even warmer and warmer, you can see they spread out to become gases. And they're moving around very rapidly as they become gases. Okay, this is number 6 in your notes. Please fill in the blank with the word other, and then pause the video, continue playing when you are ready. All right, the last thing that we need to talk about is a little bit about how this heat is actually changing these things. So first off, there's a certain amount of heat that you need to add to turn something from a solid into a liquid, and that's what's called the heat of fusion. So the heat of fusion has to do with melting, right? Melting. I know that's terrible spelling, melting, all right? So this is, the heat of fusion is a quantity. It's the amount of energy that you would need to add to turn exactly 1 gram of a certain solid into a liquid in order to melt 1 gram of something. So you can see right here, this is fusion. Fusion is melting. So to go, for example, from ice to water, the heat of fusion would need to be absorbed. You would need to add this heat to make it move faster, to make it melt. Those molecules are moving faster and can now flow. If you were to do the opposite, if you were to remove the exact same amount of heat of fusion, that would be freezing. So you can see that right here. So removing that amount of heat of fusion turns it back into a solid because you're removing all the motion, removing all the thermal energy. Now, the similar phrase here is the heat of vaporization, which if you think about the word vapor, you should think about gas, right? So heat of vaporization is a pretty easy one to remember. If you add that energy, right? So adding that energy, again, that's going to turn exactly 1 gram of liquid to gas. So that's the amount of energy needed to add to turn 1 gram of liquid to gas. For example, again, with water, if we take liquid water, add the exact amount of heat of vaporization, it will then turn into steam or into gaseous water. Again, if you remove it, do the opposite, right? So the left side here, we're removing. So if you remove that exact same amount of heat of vaporization, you'll go back to the original liquid, right? So removing that amount of energy turns it back into a liquid, 1 gram back into a liquid, okay? Now, that being said, we need to talk a little bit about what's actually happening during phase changes. So during phase changes, when we go from one phase to another, like going from a solid to a liquid or a liquid to solid, melting and freezing, or going from a liquid to gas or gas to liquid, right? That's vaporization, boiling, evaporation, or what's the reverse? Gas to liquid condensation, okay? During this time, you'll notice that the temperature, this is a measure of temperature over here, is actually staying the same. It's staying flat, right? So in these yellow parts, you can see that the temperature stays the same and it stays flat, okay? Now, the reason for this is because during phase changes, the thermal or heat energy is actually only being used to move the particles further apart from each other. So take a look. In solids, they're very close together, and in liquids, they're further apart. And in gases, they're the furthest apart, right? They're really, really far apart. Okay, so what's happening here is when we go from one phase to another, all we're doing is we're just separating those particles. We're just taking the molecules or particles and we're just moving them away from each other. But because their actual speed is not increasing, they're just moving away from each other, temperature does not increase. So temperature does not increase because they're only being separated and speed is still staying the same. So speed does not increase. Okay, now only once a substance is actually in a single phase, that's those pink parts right here, only when a substance is in an actual single phase does the thermal energy begin to actually be able to speed up the particles, which then increases temperature, right? So you can actually see increases in temperature here. And again, that's because now that it's in its single phase, it's going to actually be able to use that energy to start to speed things up. Okay, so again, during the actual phase change, that energy cannot go into speeding things up. It's only going into separating things. So what this means is that when you actually have ice and liquid water at the same time, like in a cup, the entire time that will actually stay at 0 degrees Celsius. So the entire time your cup has both ice and water, it will stay at 0 degrees Celsius. As soon as it's only the liquid, then it will begin to get warmer, right? Then it'll go up to like 23 degrees, right? Room temperature eventually. And then if you were to do the same thing and put it into water, put it into an oven, a stove, and you're to begin to heating that up, as long as you have both water and gas during boiling, it's always going to stay at 100 degrees Celsius until at some point you have only gas. Okay? All right, so at this point, we should be able to match these up. So you should know at this point what thermal energy is, right? It has to do with motion. Remember, the word thermal has to do with motion and heat. You should know what's happening during a phase change. We just talked about that. During phase changes, what's happening to temperature, what's happening to the molecules. You should be able to explain what's going on in a single phase, right? We talked about this down here. In a single phase, what's happening to the particles, what's happening to temperature. The heat of fusion, right, we talked about that up here. So during heat of fusion, what is that being used for? And then we also talked about heat of vaporization. So during heat of vaporization, what is happening to those particles there? So you can match these up on the screen here yourself, or you can do it in your notes. You do need to eventually do it in your notes. So make sure you get number 7 done, pause the video, and continue playing. If you need to, you can rewind and find any of these definitions that you need. All right, so at this point, we talked about the 3 laws of thermodynamics. We talked about thermal energy in phase changes and how that energy is actually causing a phase change, right? During phase changes, temperature doesn't change. We're just separating the molecules. Only once we're in a single phase does that energy begin to speed things up and change temperature. Okay, so at this point, make sure you rate your understanding. Make sure you think about what's one thing that you learned or reviewed today, just to make sure you reflect and understand today's lesson. And then don't forget to submit your 2C notes. Remember, it will ask you to confirm that you're submitting, so make sure you click submit twice. Thanks so much, everyone, and I will see you later.